Hello and welcome. This is SFU Math 152, Calculus 2. This is section 11.7, a strategy for testing series. So there's nothing new in this lecture. This is merely pulling together all of the techniques that we have for determining whether the infinite series that we have is convergent or not. So the way this is structured, as you will see, is there's just there's a one-page summary of all the little tests that we have. We'll just quickly go through that, and then there is a variety of questions which are taken from final exams at SFU. Actually for a while ago, but I mean nothing has really changed. These are exactly the kind of questions that we ask on exams. We give an infinite series and we ask. Does it converge or not, and why? And you need to decide which of the many methods to use to determine that and execute that and come up with the correct answer. So I'm going to go through a few of them, but this is going to be a short lecture. And for the people who are in my class at SFU, I will be posting like the fully worked out solutions to all of these questions. So I will just do a sort of kind of a few here just to make a lecture of it, but I'm not going to do them all. And for some of them, I'm just going to indicate which tests that you would use and why. And then what I expect you to do is take these questions and without recourse to the posted solutions or what I'm saying to you here, go through them, do as many as you can, and if you get stuck on one, then check out this lecture or check out the posted solutions, and you should be able to do all of these and whatever. So it's basically a bunch of practice, and so I'll do a few, but there's nothing new here. Okay, so here we are. We've got a series and we want to know, is it convergent or divergent? Here, that has been called the main question. So the main thing is to keep the main thing the main thing. Okay, and what we're going to do here is just go over what we can try. So we have an infinite series. We want to know, does it converge? So we can, first off, we could use a test for divergence. So, I mean, if the terms don't go to zero, then we're done. It diverges. If the terms of the series are positive, then we could use geometry. It might be a geometric series. It might be a p-series. It might be a telescoping series. We could use an integral test. We could use a comparison test. We could use the limit comparison test. If the terms of the series are alternating in sign, then we could use the alternating series test. This one is easy to use. So if you see alternating series, usually the alternating series test is going to be the way to go. If we've got the terms being any real number, and that this would mean, of course, that some terms could be positive and some could be negative. That's the possibility. Then what will happen is you will be possibly checking for absolute convergence, and to do that you could use the ratio test or the root test. Okay, so we're just gonna, like I said, go through a few of them here, making a few comments. So here's one here. We have the we have n times sine to the 1 over n. Okay, I'm looking at that, so I'm just going to make notes here beside the one here. So I look at this and I think, this is growing. This is bounded. I'm guessing right away that this diverges because it doesn't look like the terms approach 0, because we have something sine 1 over n, which is bounded by 1, and then we're multiplying that by n, which is completely unbounded when n gets large. So I'm guessing that this thing is going to diverge. Remember, I spoke on earlier lectures about intuition. You want to get an idea of where you're going. And so the first thing I would check here is the limit as n goes to infinity of an. So that, in fact, if you do that, you will find that that is not equal to 0. and then that tells you right away that this thing diverges. Okay, so that is using L'Hopital's rule. So that's one thing there. Okay, I see something like this, that thing there. And I find that mildly alarming because having a sign in the exponent might make it a little bit confusing to do algebra. So I immediately try to get rid of that. I look at this and I think to myself, okay, again, sign is bounded by 1. So I mean, I guess that could be sort of at a minimum subtracting 1 there, like 2 to the n. So I'm sort of thinking, okay, this could look on one side like 2 to the n minus 1, and on the other side it could look 2 to the n plus 1. I mean, that's the range. I mean, sign can go from -1 to 1. So then I think, okay, so it kind of actually basically looks like 1 over 2 to the n, so I expect convergence. So then I get that idea into my head, so then I look for something bigger. Bigger that converges, and something that's simple, right, that I can then say. So then I'm thinking to myself, okay, look for something that's bigger that converges. Immediately I see that this thing, because the denominator is as small as it's ever going to be, this thing is in fact bigger than this thing. So if I can show that this thing converges, I'm good. And I would of course write this out a little bit more formally, but I want you doing this work, so I'm just giving some of the thought process here. So then when I'm looking at this guy here, I mean, we can then sort of move to here if you need to, and that is this thing here is a geometric series. So I basically work my way through the geometric series and the comparison test. All right, next one, let's take a look. Oh, it's an alternating series. That's because of, let me just change color so it's maybe clear. It's an alternating series. So immediately I consider using the alternating series test. There's 2 things I then need to check. Is the limit as n goes to infinity of an equal to 0? Or maybe if I'm calling the whole thing an, do the terms go to, well, it doesn't actually matter. Yeah, I mean, I'm going to remove this thing when I take the limit. But so I'm saying, does the limit of the terms in absolute value go to 0? And then I'm wondering, is a n plus 1 less than a n for all n? Those are the 2 conditions that need to be met, and they are met. So this thing is convergent via the alternating series test. Okay. Again, I'm not rigorously doing these by any stretch. I am merely trying to tell you my thought process, and I want you to go through and practice. Okay, next one. Right away, alternating series test. And then what else I'm seeing here? Basically, kind of looks like this, and that converges. Well, that would be a convergent P series. So I'm expecting this thing to converge, and I'm going to use the alternating series test. Same thing. Next one. Repeat. Alternating series test. Alternating series test. Okay. And let's see which ones. Yep. Convergent. 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 So all 3 of them are. All 3 of these ones converge. Yeah. I mean, this one should be really obvious. It's alternating, and then these terms go to 0 very quickly. This one is not as obvious. Terms go to 0 much more slowly, but it's with it alternating, it's still enough. Okay, that's the first few there. Let's take a look at this one here. What am I going to do here? N factorial squared over 2n factorial. This is not so obvious, right? It's like, okay, you take n factorial and you square it. Or then you take 2 times n and you take the factorial. Which one really is growing faster? When I look at this one, it's not as obvious off the top. First of all, let's note something. We could immediately be asking ourselves this question: is 2n factorial equal to 2 factorial times n factorial? And the answer to that question is no, it is not. Okay, so you got to be careful. Like, for example, we could see a counter example. Try n is equal to 3. 2 times 3 factorial is 6 times 5 times 4 times 3 times 2 times 1, and that is some number. And then let's take a look at what is 2 factorial times 3 factorial. That is 2 times 1, 2 times 1 times 3 times 2 times 1, which is much smaller. So you can see that 2n factorial, first of all, it's not 2 factorial times n factorial, and also it's much larger. And then at this point, actually, you could actually ask yourself, then what is 3 factorial squared, to try to get some sense? That would look like this: 3 times 2 times 1 times 3 times 2 times 1. That would be 3 factorial squared. So now I know what I'm going to be looking at is this here is my denominator, right? That's when n is 3, and this here is my numerator. And I can see that, in fact, this block is the same, but this is larger than this. So I am seeing that the denominator is looks to be getting bigger faster than the numerator, but I'm going to investigate that properly. And then because of these factorials and the way this thing is set up, what occurs to me to do is to use the ratio test. So let me just set that up for you, and then you can work through the details and make sure that you can do this. So that I would take the limit as n goes to infinity of an plus 1. Okay, that's n plus 1 factorial squared divided by 2 times n plus 1 factorial, and then I would divide, that's an plus 1, and then I would divide that by an. And you know what I'm going to do? I'm going to say that you guys have practiced this a bit. I'm going to be dividing by an, so that's going to be multiplying by the reciprocal of an. Like that. Okay, that's the limit as n goes to infinity. And then now it's a matter of working well with the factorials. I will see in the numerator I'm left with n plus 1, n plus 1. That's when I handle that. And then I've got, well, let's see what I've got. I've got still left here 2n factorial, and in the denominator I've got 2n plus 2 factorial. What did I do here? I see, I'd like to be able to, I sort of need to be able to get rid of these factorials before I take the limit. So what I'm looking at here is, here, I want to somehow have some cancellation happening here. And that is going to happen by observing this in this manner. Limit as n goes to infinity. Those two n plus 1s are going to stay there. And then I'm going to have that 2n factorial. And then I'm going to look at the denominator this way. 2n plus 2 factorial looks like this. 2n plus 2 times 2n plus 1 times 2n factorial. And so I take the first two terms out from that factorial, and then that's a very nice situation because these things will cancel. And now I've got the limit down to a polynomial. I see that it's a polynomial, second degree polynomial, so I can use the ratio of the leading coefficients. In the numerator, that's going to be 1, and the denominator, that is going to be 4. So this limit will be equal to 1/4, and that is less than 1, and that tells us convergence. Okay, a little bit more detail on that one. Takes a little bit of practice to work with the factorials. We're going to see that when we start with the Taylor series for functions, the factorial is going to come up all the time. Okay, let's see this one here. I see that. Let's see. I see this here, two terms with the minus sign. And so I can see that what would happen is I would get this thing as a positive and then this thing as a negative. And then the very next value of n, this thing would show up again as a positive. So that caused me to think maybe I should use the telescoping series. Possibly I could use the integral test. Okay, so try either one of those, and you will find out that this thing here converges. Okay, let's take a look at the next one. Pi is bigger than 3. It is alternating. So then I would potentially think of checking for absolute. I could use the alternating series test, or I could say to myself, hey, it kind of just basically looks like a geometric series if I took it. I'm thinking here, check for absolute convergence. Why does that immediately spring to mind? Because if it converges absolutely, then it's going to converge. And also I see that this 3 over pi to the n is geometric. And that's easy to understand if it converges or not. And this one does converge because 3 over pi is less than 1. Okay, so the common ratio is less than 1. Okay, this one is already on the somewhere else. I see I wrote to myself here. This was obviously a question. It's alternating. I would consider the alternating series test, but this is on the spring 2002. I don't need to do it again. Okay, but it's a good candidate for the alternating series test. This is a question here asking you to say what happens for all values of p. You can't just say converges or doesn't converge. It depends on what p is. And we did this in one of the lectures. So you should be able to do for all values of p and make a little table. Try it out. And look back in the lectures. We did that. We went through the whole thing and we analyzed it for all the different values of p, and we made a table. So it does depend. So for some values of p, it converges, and for other ones, it diverges. Okay, next, where are we here? Next one. Let's take a look at this here. What does this look like? I mean, if it wasn't for this pesky little thing here, this would look like this. And when n gets large, really that plus 1 is going to make very, very little difference. So I think this looks like 1 over n, and that's the harmonic series. And then, allow me to trumpet that, the harmonic series diverges. So I would think to possibly then use the limit comparison test with 1 over n. And you'll find, in fact, that this thing diverges when you do that. Okay, I'm looking at the next one. Again, this pesky little 1 is not going to probably make much difference. It doesn't make much difference when n is large. So I'm thinking, okay, I'm looking at something that looks effectively like this, 2n squared to the 2/3, which is looking like this, 1 over the cube root of 4 times n to the 4/3. And then I know that by the p-series, when this number is bigger than 1, it converges. So I immediately think, oh, this probably converges. And I would want to do perhaps a limit comparison test with 1 over n to the 4/3, because I know that converges. And you'll indeed find out that this one converges too, because it basically looks just like that. Okay, what do we got here? We've got 2 to the n. I'm now looking at this one here. We've got 2 to the n over 3 to the n minus n. Now, it is true that n is not very small, but it is also the case that n is kind of irrelevant compared to something large like this, 3 to the n. I mean, imagine when n is 100. This is my sort of thought process. So I'm thinking, n large, and just for illustration here, 100 is not even that large, but let us see what this looks like when n is large. It looks like this: 2 to the 100 over 3 to the 100 minus 100. Okay, so this minus 100 is very, very small compared to this 3 to the 100. So then I think, okay, so this actually in fact looks like this: 2/3 to the 100. And it's not equal. Okay, it's close. It's approximately. So then here I think, well, this is kind of approximately, if you would, the sum of 2 over 3 to the n, and then I see that as a geometric series with common ratio 2/3. So I'm going for convergence, and indeed that's what will happen. Okay, just a few more. We're just kind of going through, thinking about this. Okay, here we've got 4 to the n over 3 to the 2n, and this is just a mildly, again, the minus 1 is kind of doesn't really matter. And what we want to see here is we've got 4 to the n over 3 to the 2n approximately, and then 3 to the 2n looks like it is in fact exactly this, 9 to the n. So it's important just to see that that is 9 to the n, and then you think, okay, so that then looks like this. Yeah, so I could use a limit, I can compare to that and use a limit comparison test with the infinite series 4 over n, because I know that that converges because it's geometric. Okay, let's see here. Oh, so immediately what should happen occur to you here? A limit as n goes to infinity of 1 over 2 to the 1 over n. N gets really, really large. That means this becomes close to 2 to the 0 and it's 1. So the terms don't even go to 0. You're done. Diverges by the test for divergence. Okay, maybe stop the video, right? Go through a bunch of these things now by yourself before you hear me say anything, and and then come back and get some reassurance or correct any misunderstandings. It's really important that you practice. Don't just listen to me. It's way more exciting to do the work yourself. Okay, here, so again, just kind of getting the feel for this. Which grows faster? Which grows faster, an exponential or a factorial? I mean, it's not that relevant. Which grows faster? And it is the case, in fact, that the factorial is growing faster. So, you know, even just kind of plotting something out like this for, I don't know, let's say n is equal to 5, just to get a feel for this. This would be 2 times 2 times 2 times 2 times 2, 5 of them. And then 2n factorial would be 10 factorial. This would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? And you can see it's just going to get worse as in terms that this thing is going to get, you know, bigger and bigger, and this thing is going to get bigger. Of course, exponential is still, growth is still fast, but not as fast as this factorial. So you would expect convergence, and when you see those factorials, again, a ratio test. Okay. Again, things that are bounded, you shouldn't worry about them too much when you're making your estimation. Like I see this and I'm thinking, oh no, something complicated in the denominator. But actually, let us just recall that the absolute value of the inverse tangent is simply bounded by pi by 2. So it's just something that is sitting there, but you know it's not going to be much of an effect because you're just multiplying by a number that's you know, just a little bit bigger than 1. And so really everything depends upon this, and that is n to the 3 halves, and n to the 3 halves is a convergent p series, so you would expect convergence. Okay. Finally, one here, and I think when we were doing these, I said I don't often use the root test. So far I haven't brought it up, but here I see one where we've got the nth power. So then I immediately think here, root test. root test, and indeed when you do that, you'll find it converges. Because I know when I take the root test, so we're taking a look at this, the limit as n goes to infinity of the absolute value of an, the nth root of an. So because I see the nth power here, I'm going to take the nth root. That's going to be algebraically nice. So I would head towards the root test on that. This is all a matter of experience, how many of them that you've done. Okay, we're just going to do a few more. Actually, there's not that many more, so I'll just kind of go through like this, try to finish this within, say, about 35 minutes. Okay, look at this one. Bit scary because this is not that big of a power. However, it's alternating and the terms go to 0, so this is convergent alternating series test. Okay, also alternating, and I see a power of n in the denominator. I see a power of n to the 5 halves. So when I'm first analyzing this, I think it kind of looks like n over n to the 5 halves. So what is that? That is, I subtract, that is 1 over n to the 5 halves minus 1. That is 1 over n to the 3 halves. I'm expecting, in fact, absolute convergence even, and it's alternating, so it's probably going to converge, and indeed, so you have some clues then, converge. That's what it is. Okay, next one. Oh, this looks pretty desperate, right? Exponential in the numerator, polynomial in the denominator. That's bad news, right? That's going to grow, the numerator is going to grow faster than the denominator, and so this is divergent and used like the test for divergence. I think one thing that's nice about spending a little bit of time with these infinite series is you are forced maybe a little bit to think about just what the functions look like, who's growing faster, what bounds what, so you get a feeling for what's going on. And we are in now, of course, a world, well, you don't know that, but when I'm actually recording this, it's now July of 2020. We're in a worldwide situation where the exponential growth has become, you know, very popular in the media. And to understand how fast things grow, to understand how much faster exponential growth is than polynomial growth, and how we have like an exponential growth here, and then we have logarithmic growth here. So this would be some sort of exponential growth, and this would be here some sort of logarithmic growth. And for large values of x, I mean, all of the polynomials are in here. Okay, so it is really the case. Exponential growth is, once it gets going, it goes fast, and that's actually, it's interestingly difficult for the human mind to sort of grasp that. People tend to almost always make kind of vaguely linear predictions, even when the underlying data is not linear. So it's something you want to get a nice feel for, how fast things are growing. Okay, where are we at here? Fall 2003. We are here. Let's take a look at this one here. What do we've got? Something. Well, we've got basically n times. Yeah, well, so this and this are effectively cancel one another out, and then we've got 5 to the n over 9 to the n. It's alternating for one, and so we could use alternating series tests. I'm also seeing it like that. You could also use a ratio test on this. Anyways, it is absolutely convergent. You could use alternating series tests. You could use a limit comparison test. You could use the ratio test. You also want to get a feel, you know, in something like this, when I've just told you that there's several different ways of doing it. If you can motivate yourself, do all the ways, and then say, okay, so one way took me 30 seconds, one way took me 5 minutes. Which one should I which one should I go for when I'm on a midterm? Because you really want to be efficient when you're taking a test. Okay, this thing should be deadly obvious. And high power of n here in the denominator, and it's alternating. I mean, it's clearly going to be convergent. Convergent. You use the alternating series test. You could use the integral test. All right, this one here, it basically looks like this, 1 over n squared. So you could compare with that. Use the comparison test with 1 over n squared. You also, if you wanted to spend extra time doing this and sort of, you could use the partial fraction decomposition. And then telescoping series. Would I recommend this? No, I would not, because this is going to take me way longer than it is for me to compare with 1 over n squared, which I know converges. Similarly here, I'm looking at something that looks effectively like n to the 4 over n to the 6th, which is 1 over n squared. So I would compare with 1 over n squared and determine that it converges. Okay, so its basic thing is to quickly come to what looks like the basic growth rate of the thing, and then use that information to quickly do the analysis. Okay, next one. This one's harder, right? Because I look at this and I'm like, it could potentially look a little bit like 1 over n, and then it's not just 1 over n. You've got this log n, but log n doesn't grow very fast, but then it's squared. I wonder if this is enough. So this is my thought process. My thought process is this by itself does not converge. This, for example, does converge. Is this I'm thinking here grows slowly, and so then I'm wondering, this one's not so easy for me to see. Is this enough? Is that log n squared enough extra sort of growth in the denominator to drive this thing down to 0 fast enough so that I get convergence? And it is in fact true that it is the case, but this here is a nice candidate. It converges, and it is the integral test is a nice way to show that. Okay, you can see that if you were to integrate this, you can perhaps, so let me just say now I'm looking at this and thinking of it as a function, because I'm going to use the I'm thinking of the equivalent function because I want to use the integral test, I'm thinking, and I'm wondering, as soon as I do that, can I integrate it before I even sort of really put a lot of effort into it? And then I'm thinking, oh yeah, if I make a substitution, u equals log x, then du will be 1 over x dx. So I see, oh yeah, it's going to be easy to integrate, and I'm going to be able to get the information out from the integral test. So that's a good way to go on these ones when that log is there in the denominator and you're not totally sure whether it's enough. I mean, we can make these questions, I think I did this when we talked about the integral test in the first place. Is that enough? Is this enough? Yeah. So these ones often lend themselves quite well to the integral test. Okay, final one. This one here. Let's see. What do I see here? Well, I see the factorial. I may immediately, when I see that, I might think, okay, there's a factorial there. That often lends itself nicely to the ratio test. I see it's an alternating series. Maybe I would use the alternating series test. Might be able to make that work. And then I'm looking at it before I get started. I see the factorial in the numerator and I see the exponential in the denominator. I'm guessing this is going to diverge because factorial grows faster than the exponential. So I'll be right, actually. Big surprise. So this does diverge. it diverges, you could use the test for divergence, or you could use ratio test. Possibly you could use an alternating series test. Again, try it out. Try out several of them. Get a feel for which ones are fast. Get a feel for remembering what the exact rules of the tests are. You want to just be able to do this quickly and efficiently. Okay. My final thing about this is I sometimes get students coming to me after the end of a test and saying, oh, your test was too long. And sometimes probably my test is too long. But sometimes I don't agree. And the analogy I sometimes give for that is, my test might be the equivalent of, here's the question. Yeah, you have to move from A to B. And some student will kind of basically go like this, and there they are. Voila, they've efficiently moved from A to B. And it takes up a certain amount of time. You imagine like in like a walking analogy here. And then another student kind of does this, right? And then they end up, and they did in fact move from A to B, and they got the correct answer. But of course, this extra long path that I've invented here took them a lot of time, and then they didn't have time for subsequent questions. And then they sort of justifiably say, "Oh, your test is too long. I ran out of time." But I mean, if you can imagine, if you kind of went on this path and you arrived at your friend's house late, they would say, well, why didn't you just walk here in a straight line? You would have easily been on time. So we uh, time spent thinking about efficiency is good. What you want to avoid is saying to yourself, well, when I see this, I will always use this method because I feel that give me some level of confidence. Instead, you want to have good confidence on all your tools, and you want to get to that next sort of higher level where you can look and say, I've got all my tools, and which tool should I use to get there most quickly? Because that'll really help with the when we have those timed evaluations of how well you can do this. Okay, yeah, for students taking this course with me, all of the answers to these questions will be posted, and you can check your work, and of course bring them up with me in my office hours. Thank you, and that's all for now. Bye bye.